was the midterm prep was like, this is a prep, but you can't know the answers. So if you don't get something, you're just like screwed.
I'm sorry about that, but I did take your feedback into consideration, and then I put, I made the midterm way easier.
I appreciate that because it would have been interesting otherwise, in my opinion. But
yeah, I tried to make it easier, even though it was a bit delayed on my part. So I do apologize. Let's take that one out. Let's take this one out. Let's not show you that stuff. Boop. Hello, everyone. Welcome to another 2DM3 session. Our guest lecturer is Casey. Say hello, Casey.
Hello, everyone.
So when I ask questions and nobody replies, Casey might say words.
Uh-oh.
So does anyone want to talk briefly about the midterm? Or should we move beyond that and never bring it up again? Good morning, Alexandria. Casey, when there's a 3-second silence, you speak for the class.
Well, overall, I think the midterm was pretty decent. I think I did reasonably well. I mean, I think number 15 was a little bit difficult with the new theorem and whatnot. That was like the one thing I didn't get was the first subproof. But otherwise, I think it went pretty well overall. And then I wasted a lot of time on 13 not reading the question properly. But overall, I think it was pretty good. Okay,
I'm glad. Yeah, I had a bit of a pushback that it might have been too easy with hints everywhere, but I'm glad I think it was the right level of difficulty. So
I think that was the vocal minority that found it too easy.
Yeah, so I think because of all the hints, people were able to make way more progress than they could in the previous midterms, and people could make more progress at the same time, and that crashed the system a few times, as you may have noticed. Yeah, so we did try to make up for that by extending the midterm a little bit, but unfortunately, everyone was making way too good progress and crashed the system numerous times. So hopefully we'll see how that goes. So I just want to reply a little bit to the feedback that we received. I do read that channel that I made for you guys, the feedback channel. And you are welcome to use the chat. I am looking at it right now. We can talk about some stuff that people want to talk about, but I'll also just put it right here on the side, just in case people want to read it while I talk about other stuff. So what I meant is, if you're interested in this, the person who asked, you're welcome to read it from last time. So I just want to talk about some stuff that was brought up on the feedback channel. Please, please use the format suggested in the feedback channel. What do you like? What do you dislike? And what do you want to change? Some people just had a lot of negative feedback and were not very constructive, and did not tell us if we were even doing a good job anywhere else. So I know feedback is important, but if you phrase it politely, I won't feel as bad reading it, and hopefully the other 12 TAs we have will read it too. So please do try to be polite. Some of the things people were saying was, CalcChuck is a language we're learning specifically, and we're never going to use it ever again. Does anyone here know any programming? As always, Casey, you speak for the class.
A little bit.
What are you programming, Casey?
I do mostly stuff in Python, or right now I have a 2SO3, which is Java, which is a grand old time. Nothing functional though.
So let's say you know what, you're gonna finish and you're gonna become an embedded systems programmer, and yeah, Python's great, but it's useless. It's so useless for your new job as an embedded systems programmer, because you're going to be doing probably C or assembler. You're not going to do Python. Python's great, but you're not going to do it. Does that mean your Python knowledge is a waste of time? Does that mean the effort you spent learning Python has been a waste of time?
No.
Why not, Casey? Why not?
Because you can apply that knowledge to pretty much any other language to some extent. Like the syntax may be different, but the logic is often to solve problems.
Yeah. So next term, you guys might not be doing calc-check proofs as in this purple box. You might be doing informal proofs as in this box right here. But they look so similar. And that's the point of making you do things in calc-check, to get you comfortable to do proofs without calc-check. It's like when you go to an interview and they tell you, hey, here's a whiteboard, code an algorithm for us in Python. Are you going to say, no, I don't know how to do it. I need to do it on a machine. You need both skills. They complement each other. So that's why we're using calc-check. And the input to calc-check is so similar to the informal syntax. Occasionally there's annoying things like substitutions, but otherwise it's so similar that it's more than reasonable to use calc-check, especially when you guys get immediate feedback. Can you imagine if you wrote your program, Casey, and you had to wait maybe 2-3 days for a TA to get back to you about how your program works?
Yeah, that would not be fun. That is the thing I like about calc-check, is the immediate feedback. It makes understanding things a lot easier, I think.
So somebody mentioned, is calc-check like training wheels? Can you imagine programming without using an interpreter? Can you imagine without using a compiler? Can anyone do that? So calc-check is not training wheels. Calc-check is the real deal. Can you actually show me what's going on? Right? You might not understand the underlying theory, but it is, you're showing me exactly what's going on. You've communicated that much at least. The informal proofs, like on this side, all right, you wrote a bunch of English. There's no machine to check your English, and the professor's too busy to check your English, so maybe the TA will check your English. And the TA might not be very comfortable with the material, and even if you made a mistake, the TA might not catch it. So the informal isn't ideal. Real work, real proofs are actually done in systems like calc-check. Calc-check is pretty new because calc-check lets you have English style justifications. So you can have like almost English right here. There are other systems that don't let you have English. So there's like Agda, Coq. They throw a bunch of gibberish in there and you can barely read it. So there are a lot of other systems besides calc-check, but they're much harder to use. Here you can at least use the same names in the book. You can write comments, you can do a bunch of other stuff. These real world systems like Agda and calc-check, like Coq, they don't let you do this. They're much harder to do. And there are jobs in these. So if you are interested in getting a job in Coq or Isabel to be a proof engineer, there are jobs in these things. Okay. So I just wanted to mention that. In the instructor's manual, they also, and as I said a moment ago, it's important to be able to do a lot of practice, but if there's a lot of practice, the teaching staff might not be able to mark all your work. So it's really nice that you have calc-check to give you immediate feedback, especially on the midterm, where to check your work, you just look, is it all green? If it's all green, you've checked your work, you're done, right? Doesn't that sound much better than being like, let me look over it, it's all green, I'm good to go. It compiles, it type checks, all my tests pass, right? Are there any other questions about this organization before we move on? So with regards to the feedback, we do read your stuff and we have looked at it. So we're gonna keep proof checking on. We're gonna give you the breakdown of weights that people have asked on. We have some solutions we're working on specifically for you with a lot of pros to explain what's going on. So not just here's a calculation, but rather how did we get to the calculation? What were we thinking? What did we try? What can you try? What suggestions will help you make a similar proof? Okay. So yes, we'll try to reduce the length of homeworks, maybe make them much shorter. So that's what we'll try to do. Okie dokes. You're welcome. And the plan is to go much slower. So we've talked, and we're going to try to go slower. If I go fast, please let me know either in text or somewhere else. We really do want you guys to get to improve and learn. All right. I'll go through the slides as always, and I do have a CalCheck notebook open. So I'll go through the slides slowly, and if you want, we can talk about particular pieces. And I'm happy to do that, right? So I just want to know what you guys are really into. Somebody has their microphone on. Do you wish to speak? No? Okay. So here's some rules from, I think this is the first week of class, right? Familiar rules, so nothing new. Associativity, symmetry. Then we said you can add units. Then we called that in the first assignment a monoid, and the book also calls it a monoid. And the word monoid comes up again when we talk about general quantifiers, right? So let me just open that up right here. So from last time, we said as long as you have a general quantifier, you're good to go, right? So that's what that word monoid means, just in case you forgot. It means you have an associative, a symmetric operation with an identity. That's what a commutative monoid is, okay? Nothing too fancy. You see them all the time. They're called lists, right? Without the symmetry. So they're almost lists. Then we talked about distributivity. Here's some new ones that before we didn't really show you. When C is non-zero, you can divide, right? So that's a handy-dandy result. Notice there's no division operation anywhere. What's 1 divided by 2? I think on the homework you saw the integer division operation, which would tell you 1 divided by 2 integer division is 0. So we're not going to get into that. Maybe we'll get into it in an assignment, maybe not. Trying to find out, trying to accommodate your feedback there. So maybe we'll make an assignment on division, maybe not. We'll find out. So you can only divide when pieces are non-zero and you can cancel them. But for addition, you can always cancel, right? There's no constraint. Then we talked about unary minus, and you saw this in the first assignment as well, right? We said if your monoid has an inverse operation, right, or you can have a binary inverse operation. Okay. All the elements greater than 0 are referred to as positive, and so we can define the notion of positivity axiomatically, right? And of course, it can be done in any group, ordered group. So we're going to continue talking about the integers as the book mentions, right? 2 things are positive, their sum is positive, right? So these rules, in particular the first few, are very similar to the even-odd problems you saw back in midterm 1. So nothing too difficult. And when you have access to positivity, you can then define greater than, right? So it depends if you want to start with defining these order relationships first and then get positivity, or the other way around. In the previous weeks, you saw for the natural numbers, we started by defining the order relationships inductively. It's not as easy to do for the integers because the integers are not an inductively defined data type. We'll get to what it means to be inductively defined later on in the course, hopefully, unless we decide to go a bit slower. So here's a bunch of transitivity results you've already seen. We're just going to call them one generic name, transitivity, as the book does. Some people like to give these different names, sometimes calling them absorption or Dijkstra's laws or something like that. But essentially, if you have a less than or equal to on one side and another less than or equal to on the other side, then you get the one that's stronger, Okay, so less than is definitely stronger than less than or equal to. Right? Remember, this is called weakening. So let me just write that down a little bit. Oh, sorry about that. So we said P implies P or Q, right? So we called this weakening, right? A very useful rule. And in particular, less than implies it's less than or equal to. And so in any of these ones, the relationships, you pick the one that's weaker. Okay. Is anyone confused about these four transitivity? Does anyone want to talk about them a bit more or not? Just want to make sure people are comfortable there. Okay, so you're comfortable.
Yeah, I think so.
Okay, excellent. So I'm purposely trying to go slower. I'm trying to be conscious of, not going too fast. If I am going too slow for some of you, please just ping me. If you recall, a few weeks ago, I would have just, quickly gone over this, but I'm trying to be slower. So we have these monotonicity rules. This one should really be called isotonicity, but the idea is whenever you have a plus, you can cancel that part out from both sides. Okay. For division, of course, we need it to be non-zero. Does anyone know why we don't say D is just not equal to 0? Does anyone want to try? Some interactivity in this class?
Are there negative numbers?
Yes. What would happen if D was a negative number?
Wouldn't it reverse the less than? It would be the opposite.
Exactly. So if you reverse it, for example, negative B is greater than negative A. So the order changes. This would be an antitonicity result. All right. So when D is negative, multiplication by D becomes antitonic. All right. Excellent. Good job, Kai. And then, of course, you saw trichotomy, right? Which is any two numbers are either the same or one of them is greater than the other. And of course, these are the only possibilities. And the last ones you've seen repeatedly in preparation for midterm 2. An order is reflexive and it's antisymmetric, right? Or mutual inclusion, right? So I hope people are getting more comfortable with the relaxed proof style. I do want to point out that the relaxed proof style is supposed to make life easier for you. You see a theorem statement, and then the structure of the theorem statement suggests the structure of a proof. To do so otherwise could be a bit more involved. Right? So I know some people were thinking, do I have to do the relaxed style? You don't have to do anything you don't want to, right? In life, no one can force you to do what you don't want, but the cost of doing things in a way that you decide is that you have to deal with the consequences. Right? So Lynn asked a good question, and so hopefully we'll work a little bit down, and I do have some monotonicity and instantiation, so we'll work a little bit down and we'll get to it, all right? So again, you can prove theorems however you want, but the consequences of your decisions might mean the choices you make might be suboptimal. Might be much more difficult to prove things if you start off in a wrong direction. So hopefully we're gonna get you some partial solutions later this week that will have detailed mind dumps about what we're thinking as we're making the proof, and hopefully that will guide you as well. Okay, ducks. So right here, so let's just talk about it. How did you choose the cases? Right here, we're talking about the positivity of B times B, and we know that B is not 0. Okay, well, a moment ago, we said the only possibilities for numbers are that numbers are either equal or greater than. So if it's not 0, that means it's either less than 0 or greater than 0, right? Less than 0 means that we have a case it's not positive, and greater than 0 means we have a case it is positive. So we're going to do two cases on these two possibilities. Everything either is or is not. B either is positive or it's not positive. Okay. So completeness means one of these scenarios actually has to happen. So when I'm talking about B, I know that it's always going to be either positive or not positive, right? This is the law of the excluded middle. Everything is either true or not true, right? So completeness just means the cases you're talking about, are they actually possible or not? Right? Do they cover all possible scenarios? Right? Yes. So you're saying I have this scenario and this scenario and that scenario, and in each one I can proceed in a particular direction. Great. That's what your case proofs do. But is any of these scenarios actually going to happen? Right? So for example, I'm going to get a car, and if my car is black, I will cut my hair, and if my car is red, I will cut my hair, and so whatever color car I get, I will cut my hair. Not really. I will only cut my hair if it's black or red. The other colors, we didn't consider them. We only considered two scenarios out of the many possible scenarios. So that's what completeness means. It means, have you considered all possible scenarios or not? Right. So in this case, we're saying there are two possible scenarios. Either B is positive or B is not positive. And when we can show that when P is positive, the theorem is true. And when P is not positive, the theorem is still true. So we showed that there are only two possible scenarios, and it doesn't matter which scenario we're in, the theorem is going to be true. Okay, next. All right, excellent. And all right, okay, excellent. Okay. Yes, exactly. Completeness is you're covering all of the possible cases. That's all it is, right? It's like you're doing a proof by induction, and you forgot to do a base case or the inductive step. You need both of the pieces. So case analysis for numbers is actually weaker than induction. Induction implies case analysis for numbers, but that's a story for another time. Okay, next. So here we just use the by clause, which you're always welcome to do, but you can also do an actual calculation, right? I suggest you do calculations unless you're actually comfortable with using by clauses. So let's move on to the thing that some people seem to be afraid about, and we'll talk about monotone city here as well. All right, so someone just asked again, why is it complete? So law of the excluded middle just says either the thing is true or the thing is not true, right? So completeness means you have to show that one or the other of the cases is gonna happen. So you say, here's the first, sorry. Sorry. You say, here's the first case, right? Or the second case, and I need to show that this one or this one or this one or this one of them at least will happen. And so their disjunction is true. The ORing of all possible cases is going to be true. Okay, that's all right, great. Okay, so let's talk a little bit about quantification. So I think this is the third time we're talking about the idea of you have small operations, small binary operations, and then you can extend them to the bigger ones, small to big, small to big, small to big, right? Nothing too radical. This is just a convention that's been adopted throughout mathematics. Plus, when it quantifies, becomes sigma or sideways m. Times, when it's quantified, becomes capital pi. And when it's quantified, becomes this upside down a, or becomes this backwards e. Okay. And the other ones usually don't have, they just make the symbol bigger. Okay, that's. So as I said at the beginning, in general, we're going to be working in a commutative monoid, right? And as always, you have the quantifier, then your variables, then the constraints, and then the body, right? And it's somewhat familiar to initializing your variables, having a loop condition, and then an iteration body for the loop. Okay. So as we said before, the idea is that quantifiers are a theory of loops. They are a theory. There are multiple ways to think of loops, and loops implement quantifiers. So in particular, the empty range rule says if the loop never runs, then you're at the initial values. The 1-point rule says if the loop runs but only once, then you can get rid of the loop and just put in the body with the one possibility in there. Right? Split off term says when you're executing a loop, first you do one run of the body, and then you do the rest of the loop. So you do one run of the body, and then you do the rest of the loop. Okay. All kinds of loops can be represented by quantifiers. So if you think of nested loops, that's when you have multiple variables. Instead of just I, you have I comma j. If you want to have a loop with like a break in the middle, then what you do is you say inside the body, you put a condition that says, hey, if this thing is met, we just return 0 rest on. So you can mimic break loop things that way. If you want to have a continue, for a continue loop, then you can augment the constraint. So if you think of a loop, you can write it down as a quantifier. Okay, dokes. Good question. You may, in second or third year, talk about primitive recursion, and then you'll see quantifiers again, but then they'll be called folds, F-O-L-D, which is a fancy word from functional programming, and you might see that again, and then you might be able to prove certain things about computability using them. Yeah. And the last one we talked about last time was this range split rule, right? If you have two different pieces that your loop is considering, then it can consider the first piece, then it can consider the second piece, but then the second piece might repeat parts from the first piece. So this only works if there is no overlapping, okay? Otherwise, you repeat pieces. Alrighty. We talked last time about if you have a duck and you named your duck Obama, and then when someone says Obama, that's with reference to your duck, because we're all talking about a noun Obama that designates the creature owned by you, your duck. And that was the idea of scope. When I say Justin, do I mean Justin Bieber or Justin Trudeau? Right. So this was the idea of scope, and we said we use parentheses to delimit scope. So the I outside here is like is Obama the president. I over here is Obama the duck, right? So it depends on your scope. Okay. We talked about textual substitution. We said if you try to substitute and you do it incorrectly, then suddenly the if you substitute if you try to substitute x with the expression f everywhere, if f contains the name y, then on the right-hand side you'll suddenly have more y's than the left-hand side does. Okay, so this quantifier, remember the dummy variable doesn't really matter. If you're looping over I or looping over j, doesn't really matter. So if I change all the y's here to j's, and this one now introduces a y, and here I decide to change all y's to j's, I have an extra j here than I do on the other side. Okay. So not a just a technicality, a subtlety. So the idea of talking about substitution rules is some of you, a large number of you, will continue in the computer science stream, and then the idea is you have a loop. How does your loop execute? Your loop executes by doing substitutions repeatedly. Right? If you call a function body, and then the function body has a loop inside it, then substitution has to occur. Okay, so if you get into the 4th year compilers class, then you'll actually have to write some of these manually by yourself. For now, we're just talking about them abstractly a little bit, but this is a fundamental feature of an aspect of computing. Okay, so I know sometimes students think, oh, we're doing stuff that's so far removed from computing, but quantifiers are loops. Substitution is evaluation. Okay, so nothing unreasonable, and hopefully all practical. So here's an example of renaming. Right, we everywhere here it's X. We decide to change everything to Y. To Z. Right, and then we finally perform the substitution. Okay. We need to perform the substitution because there's an X here, and we said the dummy variable name doesn't actually matter. Okay, so we need to change that. Okay, ducks. So let's look at a few more examples, and maybe we can try some stuff on CalcCheck. So here's another one. Remember, X as a dummy, as a quantifier name doesn't really matter, but now we're going to introduce a new X. Okay. So let's first change the dummy name. That doesn't matter. Excellent. Now we can perform the substitution. And the substitution says replace every X with Y plus X. But there's no X's in here. Okay. And if we want, we can change the expression back. All right. So let's try to make, so what I want to show you by this example is in a quantified expression, such as this one, quantifying over X, there is no X. It's like the Matrix. There is no spoon. There is no X, right? And again, some of you that will end up taking advanced computing science will see that variables are really annoying because of this feature. And so there's a thing called De Broglie indices, where instead of using variables, you use numbers. So this X goes away, and here we put the number 0, and everywhere you see X, you put the number 0, okay? The further away the variable, the bigger the number that represents it. So there is no bound variables. You do not see them. Okay. So here we're substituting X becomes Y plus X, but there is no X, and so we just end up here. Okay. Yes. Yes. In this case, it's to substitute or not to substitute. Okay. If X does not occur, then the substitution leaves it alone. Okay. There is no X in here, and so substitution leaves it alone. Okay. Which, yeah. Okay. So the rule that lets you rename things. Well, sorry, I think there was a question here. No, even if there was an X in the body, it would not matter. Even if there was an X right here in the body, because you can rename the variables, and then if there was any X, it would become a Z, right? And because there's a Z, that's not an X, you try to do this substitution, and there is no X, and so there's only Zs, and so there's no X anywhere, right? So I hope that, does that clarify, Mark? If you have questions, please let me know. All right. So the ability to rename is called alpha renaming or alpha conversion. So Lynn asked, what's the point of doing that? The point of doing that is, so Lynn, we want to perform this substitution, okay? Someone made a function call, and our function call has a loop, and our loop is a quantifier, and a function call is a textual substitution. So we need to evaluate this, okay? So how do we evaluate that? Well, a substitution says, everywhere you see an X, replace it by Y plus X, okay? But substitution for quantifiers says, this name is not allowed to occur in the new substituted expression. So first, we have to get rid of X everywhere. So we change it into a Z. Now that it's a Z, there is no Z anywhere here, so we can perform the substitution. When we perform the substitution, we replace X's by this expression. There are no X's. And now, just for convenience, we're going to rename all the z's back to x's. Okay, so that's why you need to do it this way. Was that clear, Lynn? I'm glad. Good. Yes, please ask questions. I would like you to make use of lecture to ask on the spot, especially because then we record them for you and you can watch it again later and it's your question and other people can benefit. So please try to ask. No problem. That's why we're learning. No problem. All right. So here is the rule that lets you change names. It's called alpha renaming or alpha conversion. So you might see it again in computing. A lot of times there will be some quantifiers like a for all or a sum, and then the teacher will change the variable and they'll be like, oh, variable names don't matter, and they'll just change it. And the justification is this rule called alpha conversion. Okay. So you'll see people being like, names don't matter, and local names don't matter, just change them. So that's the idea. It's called alpha renaming or alpha conversion or dummy renaming. So you might see this to come up repeatedly. Okay, next. So here's the example where we rename I to J. Okay, so this I becomes a J, and everywhere I see an I, it becomes a J. Okay, here we're trying to rename I to K, but what's the problem? Here there's only one K, here's 3 Ks. So we've changed the number of times K occurs, and so it clearly can't be the same, right? Something must have gone wrong, okay? So dummy renaming says when you try to make the new name can't already be around. It has to be fresh, right? The new name can't already be nearby. It's got to be a fresh new name. Okay, ducks? No worries, no worries. Okay. So that's the constraint there, right? So maybe I'll just put that as a comment for going forward. 821. When changing the dummy name, it needs to be fresh new name. Okay. And so the last piece we didn't get to last time was this idea of Leibniz. So this is kind of the new thing now, right? So it's okay. We took a while to get here. That's not a problem. So if you recall, we have Leibniz, which is equals for equals. If we try to use this equation, x plus x equals 2 times x, we can't use it here because there's an x right here that we didn't substitute. There's an x right here we didn't substitute, and then there's 2 more x's we didn't substitute. So we did not really do equals for equals because it renames the x, right? So instead, we have this just technically different form, which says when you have equals for equals, you do them inside the range, or you do them inside the body. Okay, so it's just a small technicality. There's nothing really deep here. It's just when you're substituting equals for equals, your equal expressions they can be aware of x. Okay, your equal expressions are aware of x. Right, so it's nothing new. It's going to be used implicitly, right? The only thing that you need to, as always, is to show the underlying equality. Right? So nothing deep. Okay, ducks. So here's where we get to some new cool stuff, some really juicy things. So the first one, somebody was asking about all kinds of loops. So this is called interchange of dummies. Right? If you have 2 nested loops and you realize they don't depend on each other, then you can change the order of your loops. Isn't that pretty cool? All right. So imagine you have a for loop depending on y, and you have another for loop, okay? The parent loop that depends on x, and you know that s doesn't depend on x at all right? S doesn't mention x, right? That's what the provider says. It says these guys are independent. Then you can change the order of your loops. So a lot of times, in particular in Python, you'll have nested loops, right, indented all the way. And sometimes you don't know when I can change the order of my nesting, and this rule tells you to, right? The second rule says, hey, maybe you've nested them and you realize, wait a minute, this nesting is silly. Why don't I just have 2 variables and I'll just collect their constraints together, right? Like I'm looping independently. All right, I'll just have one loop that loops over both of them at the same time, right? And I do that way, right? It's just easier to express, right? If your code isn't so big, you're less likely to make an error, right? But can S mention Y on the left-hand side of 819? No, S cannot mention Y. Sorry, S definitely can mention Y. The constraint is that S doesn't depend on X. X does not occur in S, okay? So S can definitely have Y in it, and R can definitely have X in it, but then to move it over here, if S mentioned X, this would not make sense. How can S talk about X when X is later on? So that's what the constraint is. It's make sure you don't introduce extra names when you swap them around. Okay. All right. And then the last one we talked about briefly. You're welcome, Jay. And the last one we talked about briefly was dummy renaming. Okay. And so hopefully you've seen these rules and you know that they're useful. The last one is just a technicality. It says if you have X and Y, that's just Y and X. Okay, so it's not a big thing, right? This does matter if you decide to do advanced logic or advanced computing. Then this permutation is a very subtle thing. But in practice, it doesn't, If I have X comma Y or Y comma X, it's not a big deal. Okay, so you won't find this one in the book. So we've added it to the list. And likewise for all and for exists, as usual. Okay, so now we're going to get to some interesting ones as well. And maybe we can do some calc trick if we have time. So this one is called distributivity, right? And if you recall, so here's an operation. You think of everything over there as an operation. And here's an expression, P times Q. And then I distribute all of the syntax onto P and onto Q. And that's what we have over here. The syntax is distributed to P, and then the syntax is distributed to Q. And it's called the distributivity rule. Okay. And the idea is when your body is do 2 pieces at once, you can do one after the other, right? You might have seen this sometimes in your code if you're programming a lot. You have a loop, and then right afterwards you have another loop, and they loop over the same domain. They loop over the same stuff. Then you can fuse your loops, right? And they still go over the same domain, and you just do both computations over the same thing. So this is loop fusion, right? So this one is very popular among programmers. If you Google loop fusion, you'll see various forms of this. So let me just add this one to our list. Distributivity. Loop fusion. Okay. So if you decide to get into compiler theory, you will undoubtedly implement some of these yourself in the guise of quantifiers. Good stuff. There is an important thing to mention, though. Infinite quantifications are usually not defined. If you have a loop like this is a loop over all integers, and we're going to sum them all up. There's infinitely many, so your loop is not going to terminate. So we are trying to be practical in this class. So we are showing you, hey, you can have non-terminating loops, and you need to be careful about that. If they don't terminate, you can't really reason about them. So we do allow you guys to write these things down, and we want to let you know you might see them. If you remember from calculus, there are ways to talk about infinite sums. but in general, an infinite loop is very generic. So in some cases, we can tell you when it terminates and when it's not. In particular, and or are always defined, and we'll get to that in a little bit, hopefully. Let me see what someone asked. So this has to be a star quantifier. This has to be a star, and this one has to be a star. They have to be the same kind of operation that's being accumulated as you loop. Okay. Does that help, Eamon? All right. So yeah. Okay. Great. The reason that quantifications over and or are always defined, hand wavy, is because and or are idempotent. So if I see P and P and P and P and P, well, P and P is just P, right? So idempotence is the insight there. We can come back to it. I just want to get to the range split rules. So we talked about them, and maybe we can come back to it if people are interested, or we can discuss them in detail in the online forum. So range split rules. We talked about before about if you're working over a union of data streams, you can split that up into one piece and then another piece, right? But they have to be disjoint. There's no overlapping, right? Today, we're going to talk about this form, 817. So 817, I'll just write it down for you. You've already seen it before. It's 817. Many of you may have seen it in grade 11 data management. It's called the principle of inclusion exclusion. Right. So the idea is, if I'm working over a data stream, and at the same time I also consider all possible duplicates, then that's the same thing as if I did one piece, then I did the other piece. Because if there's possible duplicates, they've already been accounted for in the left-hand side. So here we said, if you do R, if you do the first piece, and then this one has duplicates, then the duplicates are not accounted for on the left-hand side. But now we just say, let's account for the duplicates. Okay. Now the principle of inclusion exclusion, as you may have seen it, for example, in probability theory, says if you have the probability of X union Y is the same thing as the probability of X plus the probability of Y minus the probability of X intersection with Y. So you may have seen it this way, and we're just moving that minus to the other side because we're saying we're in a commutative monoid, and in a commutative monoid you might not have a minus, so it's equal to bring it to the other side. Just wanted to mention that as I'm running a bit short on time. Does anyone have any questions about 817? Let's do a quick little calculation, or not. Does anyone want to do a quick little calculation with 817? Is anyone there?
Yes.
Yeah, sure.
All right. Do you guys want me to use this fancy star, or do you want me to use something like sigma or for all? What would you like to see? All right. Which operation would you like? Either or. All right, sure. Let's do claim. 816 is derivable from 817. Whoa. Okay. Just we're running a bit short on time, and I feel we haven't really done any calculations, and so let's try to do one really quickly. So here's the sum. Let's start off with 817 says. So just to make things even easier, here's true, and then this is 817. 817 says if you have the sum with R or S, spot P plus / the sum of X with R and S, spot P. Okay. Sorry, 817 says all of this Sorry, what we're trying to show 816. So we need this one right here, Command V. Okay. All right. So assumption is that R and S is equal to false, right? This is our assumption. But before we can make use of that, we're gonna say identity of plus to introduce a 0, and then we'll say empty range for sigma to get this thing. Command C. But here we have a false. Sorry, I'm running out of time, and I just want to show you this little thing. And then our assumption is that R and S is false, so we can take this whole thing and replace this by R and S. And now we can finally apply 817, and 817 says do R and do S. Cool. Okay. So I just wanted to show you that you can get 816 from 817. When they're really disjoint, you can get one from the other. So hopefully we'll continue back here tomorrow. If you want me to be slower or faster, please let me know. I hope you have a terrific Thursday, and I'll be in the chats for a little bit if anyone wants to ask me questions. Yeah, goodbye to everyone else. Take care.